Welcome to Mastermind e-Learning, Physics for Wassce students. Today we shall look at the topic electronics. At the end of this lesson, you will be able to distinguish between conductors, semiconductors, and insulators. You will also be able to describe the band theory explanation for electrical conduction in conductors, semiconductors, and insulators. Distinguish between intrinsic and extrinsic semiconductors. Explain the production of p-type and n-type semiconductors. You will also be able to describe the formation of a p-n junction, and you'll be able to explain the characteristics of a p-n junction diode. What is electronics? Electronics is the branch of physics that deals with the study of the flow and control of electrons and their behavior and effects in vacuum, gases, and semiconductors, and with devices using such electrons. You'll find a lot of electronic devices around, and they have their underlying on this area. It is important to note that the mobile phones, the television sets we use, and a lot of the gadgets we use around are based on electronics. We shall do a quick review. Matter consists of atoms. These atoms have a nucleus, and there is a shell around the nucleus around which electrons move. This nucleus has protons and neutrons in it, and the nucleus is very, very dense. Now, there is a force of attraction between the electrons and the nucleus. The closer the electrons are to the nucleus, the greater the force of attraction, and vice versa. It means that the farther away the electrons are from the nucleus, the lesser the force of attraction. And so it is very easy to remove an electron that is far away from the nucleus than it is to remove an electron that is closer to the nucleus. So then it makes it very difficult to remove an electron that is closer to the nucleus. Solids may be classified in terms of their resistivity or conductivity as conductors, insulators, and semiconductors. What is a conductor? These allow electric current to flow through them easily, and this is due to the presence of free electrons. Now, conductors are materials which have very low resistivity and high conductivity. Examples of conductors are copper, aluminium, and most metals. The second type of solid we shall look at is the insulator. Now, these are materials which do not allow electricity or electric current to pass through them easily due to the absence of free electrons. Now, insulators do the opposite of a conductor in that they have a high resistivity and a low conductivity. Examples of insulators are wood, plastic, concrete wall. You can think of others which are not listed here, some like paper. Valence electrons. The number of electrons present in an atom are distributed among the various shells. Each particular shell has a particular holding capacity. So the first shell can take 2, the second shell can take 8, the third shell can take a particular holding capacity. The electrons that exist in the most outermost shell are known as valence electrons. Based on the valence electrons, you can classify atoms as either monovalent, divalent, trivalent, tetravalent, or pentavalent. Monovalent elements or atoms have only one electron in their outermost shell. Examples of monovalent elements are lithium and sodium. Divalent elements, these have 2 electrons in their outermost shells. Examples are magnesium and calcium. Trivalent elements, that they have 3 electrons in their outermost shell. Examples: aluminium, boron, gallium, and indium. Tetravalent have 4 electrons in their valence shells, and then pentavalent elements have 5 electrons in their outermost shell. You can see the prefixes mono, di, tri, tetra, and penta. These are prefixes which respectively mean 1, 2, 3, 4, 5. So it will help you to tell how many electrons are in the outermost shell of the particular element or atom. The energy band theory. Before I look at the energy band theory, I'll need you to remember that semiconductors are materials whose resistivity and conductivity lie between that of a conductor and an insulator. Energy band theory. In single isolated atoms, the electrons are in orbit at specific energy levels. When groups of atoms are brought together, for example, as in the case of solids, so the outermost energy levels of the electrons in the outermost orbits of the neighboring atoms overlap each other. When you now come and put all these atoms together, the outermost shells, subshells, and then the orbitals merge. They merge together, providing a greater number of available energy levels for the electrons to inhabit. When large numbers of atoms are close to each other, these available energy levels form a nearly continuous band in which the electrons can move, and this is what we call the energy band. An electron in a solid can only have an energy that falls within one of these energy bands. This phenomenon is what has led to the formation of energy bands, and we call this the energy band theory or the band theory. 3 types of energy bands are formed when the outermost energy levels overlap with each other. Now, these are the valence band, the conduction band, and the forbidden gap. Now, this is a simple diagram of the conduction band, forbidden gap, and the valence band. You can see that the forbidden gap lies between the conduction band and the valence band for a specific reason. On the vertical axis is the band energy, on the horizontal axis is the energy band in the conductors. Let's look at these bands individually. The valence band, it is the cluster of lower energy levels and accommodates all the electrons, including the valence electrons. Okay, so at this band, you find the valence electrons. It is a cluster of the lower energy levels. It is the band of electron orbitals that electrons can jump out of and move into the conduction band when excited. Now, electrons in this band do not contribute to conduction, as conduction requires a definite, specified amount of energy. The valence band is formed below the conduction band, as shown in the figure above. We looked at a diagram earlier. You can see that the valence band is below the conduction band. The highest energy level which can be occupied by an electron in the valence band at 0 Kelvin is called the Fermi level. It's called the Fermi level, the conduction band. It is formed by higher energy levels as compared to the valence band. So remember, we said the valence band is formed by lower energy levels. We are saying that the conduction band is formed by higher energy levels. Now, at higher temperatures, the valence electrons escape out of the valence band to enter the conduction band and become free electrons. These free electrons are then responsible for the conduction. The conduction band has higher energy than the valence band. Electrons in the conduction band are called free electrons, conduction electrons. Now, excited electrons jump from the valence band into the conduction band. When electrons are in these orbitals, they have enough energy to move freely in the material. The greater the number of electrons in the conduction band, the higher the conductivity. The forbidden gap. Now, it is the gap between the valence band and the conduction band where no electrons can exist. Remember, no electron can exist in the forbidden gap, hence the name forbidden gap. Electrons are forbidden from existing over there. The width of this gap is different for conductors, semiconductors, and insulators. Factors which affect the conductivity of a semiconductor. Number one is temperature. Remember, I said that for a semiconductor, its conductivity and resistivity lies between that of a conductor and an insulator. So it is not a conductor, it is not an insulator. But with a little push, it can become a conductor. And with a little push, it can become an insulator. One of the factors that can affect the conductivity of a semiconductor is its temperature. An increase in temperature results in an increase in conductivity and a decrease in resistivity. Remember that conductivity and resistivity are inversely proportional, meaning that as conductivity is increasing, resistivity is decreasing, and vice versa. When temperature increases, the electrons gain more energy to jump into the conduction band. More free electrons and holes are created in the conduction band, and hence the higher conductivity of the semiconductor. Now, number two is impurities. When you introduce impurities, it affects the conductivity of the semiconductor. So when the right amount of a different element known as the impurity is introduced into a semiconductor, its conductivity increases. The introduction of an impurity increases the number of free electrons and holes present. So hence there's an increase in the number of minority and majority charge carriers. The effect of temperature on conductors. In conductors, no forbidden gap is present between the conduction band and the valence band. The conduction band and the valence band overlap each other. The valence electrons are loosely bound to the nucleus in conductors. When an electric current is applied, the localized electrons are free to move within the structure. This is the case that happens in normal temperature. It means that when I increase the temperature, the electrons in the valence band become more excited and they can easily move into the conduction band to go and aid in conductivity. So when the temperature increases, the atoms start to vibrate with higher amplitude because they have gained more energy. These vibrations causes frequent collisions between the free electrons and the other electrons. Each collision drains out some energy of the free electrons and it restricts the movement of the localized electrons. So this means that the resistivity of the metal increases. When the resistivity increases, the conductivity of the material decreases. Okay, so metals or conductors have a positive temperature coefficient. Examples for positive coefficient materials include silver, copper, and gold. You can see that as temperature increases, resistivity slowly also increases. In insulators, the forbidden gap between the conduction band and the valence band is very wide. So it means that more energy is required before electrons can jump from the valence band into the conduction band. Now, the valence band is completely filled with the electrons. When the temperature is increased, the atoms vibrate and it makes the valence electrons present in the valence band to move into the conduction band. This in turn increases the conductivity of the material. When the conductivity of the material increases, it means that the resistivity decreases and so the current flow increases. Some insulators at room temperature changes to conductors at very high temperatures. So it means that insulators have negative temperature coefficients. The effect of temperature on semiconductors. In semiconductors, the forbidden gap between the conduction band and the valence band is very small. I told you its resistivity and conductivity lies between that of a conductor and an insulator. At 0 Kelvin, the valence band is completely filled and the conduction band may be empty. But when a small amount of energy is applied, the electrons easily move into the conduction band. When the temperature is increased, the forbidden gap reduces in size and the electrons move from the valence band to the conduction band. This increases the conductivity of the material. So for semiconductors, it is said that they have a negative temperature coefficient. A negative temperature coefficient. So this is a graph of resistivity against temperature. You can see that as temperature increases, the resistivity decreases. Now let's look at what we call charge carriers. Conduction is only possible in the conduction band due to the availability of free electrons. When an electron leaves the valence band, there will be a loss of one negative charge, since an electron is a negatively charged particle. The vacancy that is created when the electron leaves that place, we call that vacancy the hole. This hole has a positive charge. The number of holes created in the valence band depends on the number of electrons liberated from the valence band. Remember, I mentioned earlier that when the electrons get excited at the valence band, then they move into the conduction band. Now we are saying that when these electrons have moved, they leave a hole over there. That hole we are saying is also a charge carrier. So both positive holes and negative electrons are responsible for the conduction process and are known as charge carriers. Carriers which are more in number in a particular band are known as majority charge carriers, and those that are less in number are known as minority charge carriers. Doping is the process whereby an impurity is introduced deliberately into a pure semiconductor in its right proportion in order to improve its electrical conductivity. So an impurity does not always mean something bad. Under electronics, when we talk about an impurity, we are talking about introducing a foreign material into the original material or the present material. So if I have, let's say, a germanium piece and then I add, for example, arsenic to it, the arsenic is the impurity and the germanium is the original material. The added impurity is called a doping agent. So if I had germanium and I added arsenic, arsenic will be the doping agent. There are two types of semiconductors. We have the intrinsic semiconductor and the extrinsic semiconductor. Let's look at the intrinsic semiconductor. It is a semiconductor in its pure state without impurities. A semiconductor in its pure state without impurities. And the number of holes are equal to the number of electrons. In other words, it is an undoped semiconductor. So when you have not added any impurity at all to a particular semiconductor, we say it is an intrinsic semiconductor because it is in its pure state. Examples of intrinsic semiconductors are germanium and silicon in their pure state. The second type of semiconductor is called the extrinsic semiconductor. It is a semiconductor that has been doped in such a way that there is an unequal number of holes and free electrons. So in here, notice that an impurity has been introduced. Based on the type of impurity that is introduced, then we are going to have more holes or more electrons. So when an intrinsic semiconductor is doped, an extrinsic semiconductor is obtained. And these extrinsic semiconductors, they are what are applied in electronic devices that we call thyristors, transistors, diodes, etc. We shall look at that in further lessons. Now, the electrical characteristics of an extrinsic semiconductor varies per the level of doping. How much doping did you apply? That will affect the conductivity you have or the resistivity you have. There are two types of extrinsic semiconductors, and these are N-type semiconductors and P-type semiconductors. Let's look at N-type semiconductors. It is an extrinsic semiconductor which has been doped with a pentavalent impurity such that the free electrons are the majority charge carriers and the holes are the minority charge carriers. When I have doped a pure semiconductor such that my free electrons become the majority charge carriers and my holes become the minority charge carriers. We say that I have an N-type semiconductor. N here means negative. And remember, we said the electrons are negatively charged. And so we pick the N and we say that N-type semiconductor, meaning that the negatively charged carriers are the majority charge carriers over there. Now, how are N-type semiconductors formed? So to form an N-type semiconductor, you pick a tetravalent element and you dope it with a pentavalent element. When a pentavalent element, such as phosphorus or antimony, is used to dope a tetravalent element such as germanium, an N-type semiconductor is formed. So remember, you pick a tetravalent element and you dope it with a pentavalent element, and then an N-type semiconductor is formed. What is happening in, you notice that this is a germanium piece, then it is doped with arsenic, which is pentavalent, the germanium is tetravalent, and you dope it with arsenic, which is pentavalent. Now, the pentavalence means that it has 5 valence electrons. So you see that the arsenic bonds with its neighboring electrons so that it forms 4 covalent bonds on either side. 1 electron is left, which is free to move about. We are saying that this free electron is quite loosely bound to the nucleus, and so it becomes free and it goes to aid in conduction. The electron, since it moves away from the valence band to donate 1 electron in the conduction band, is known as the donor electron or the donor impurity. The donor electron or the donor impurity. When a pentavalent impurity is added to a pure crystal, it produces free electrons. P-type semiconductor. It is an extrinsic semiconductor which has been doped with a trivalent impurity such that holes are the majority charge carriers and the electrons are the minority charge carriers. Remember we said that in N-type semiconductor, a tetravalent material is doped with a pentavalent material. Now here we are saying under P-type semiconductors that a tetravalent material is doped with a trivalent material. When trivalent elements such as boron, aluminum, or gallium, or cobalt, or indium are used to dope a tetravalent element such as germanium, a P-type semiconductor is created. Here we have a germanium piece. It is doped with boron, which is a trivalent piece. You see that it forms 3 covalent bonds on either side, but because it is trivalent, it will not have an electron to bond with the germanium on this side. So a hole is created. We are saying that these holes contribute to conduction. And so here you see that if you dope it with more boron, it means that more holes will be floating in this piece. And we said that holes are positively charged. And so we are going to have what we call a positive type conductor. So the positive there goes to represent the hole which is positively charged. When a trivalent element such as boron is used to dope a pure germanium crystal, the boron atom, which has 3 valence electrons, replaces 1 germanium atom in the crystal lattice. The 3 valence electrons of the boron form 3 covalent bonds with the 3 valence electrons of the 3 adjacent germanium atoms. 1 germanium atom of the crystal lattice has an extra valence electron which is not bonded. As soon as this electron escapes, it creates a hole in the valence band for an electron to occupy. This hole is positively charged. This hole can accept an extra electron to counterbalance it. We call a piece an acceptor atom. Okay, so we say that it is an acceptor atom, or the boron is an acceptor atom. Now let's go on to look at the p-n junction. A p-n junction is formed when you join the p-type semiconductor and the n-type semiconductor together. A p-type semiconductor has holes as its majority charge carriers, whilst the n-type semiconductor has electrons as its majority charge carriers. On their own, these 2 types of semiconductors are neutral. They are electrically neutral. However, when we join these 2 together, they behave differently and produce what is known as a p-n junction. A p-n junction is the basic building block of many semiconductor devices like diodes and transistors. How is a p-n junction formed? When the N-type semiconductor and P-type semiconductor are first joined together, a very large density gradient exists between both sides of the p-n junction. With the formation of a p-n junction, the free electrons present at the edge of the N-type semiconductor try to move into the p-type region. Remember, positive and negative attract, and so the holes also on the p-type region try to move into the n-type region. This process continues back and forth until the number of holes and electrons which have crossed the junction have a large enough electrical charge to repel or prevent any more charge carriers from crossing over the junction. So eventually a state of equilibrium will occur, producing what we call a potential barrier around the junction. Okay, so we are saying that more holes will try to cross to the n-type region, electrons will try to cross to the p-type region, to up to a point where something we call a potential barrier is created at the junction. Since no free charge carriers can rest in a position where there is a potential barrier, the regions on either side of the junction now become completely depleted of any more free charge carriers in comparison to the n and p-type materials further away from the junction. This area around the p-n junction is what we call the depletion layer. P-n junction is also known as p-n diodes or junction diodes. As you can see in the diagram here, these are n-type region, a p-type region. This is our depletion layer, because a potential barrier has been created over here. There can be no more diffusion of holes and electrons into the respective region. The working definition for a depletion layer is a narrow region across the p-n junction where electrons, which are majority charge carriers in the n-type semiconductor, and holes, which are majority charge carriers in the p-type semiconductor, recombine and neutralize. The presence of the depletion layer opposes conduction in the p-n junction. So at the neutral condition of the barrier, the net current flow is zero because of the presence of equal and opposite currents or charge carriers. The depletion layer, because it is opposing the flow of currents, one would want to be able to do something about it. Now, the width of the depletion layer is inversely proportional to temperature and applied voltage, which means that when I increase the temperature, the width will reduce. When I increase the applied voltage, the width will reduce, and vice versa. So the working definition for a potential barrier is that it is the opposite potential difference that tends to prevent the diffusion of holes and electrons across the p-n junction. This brings us to the end of Electronics 1. I hope you join us for Electronics 2. Don't forget to subscribe to our channel Mastermind e-Learning. Thank you.